Welcome back. Today, we're doing a deep dive into, well, a pivotal moment. J.J. Thomson's 1906 Nobel Lecture. Our mission, really, is to unpack how he showed everyone that the atom wasn't the fundamental building block they thought it was. He found something smaller, the corpuscle.
Which we now call the electron, of course. And you really can't underestimate how revolutionary this was. I mean, physics was deeply divided.
Right, about cathode rays. Were they particles like the English tended to think?
Or were they some kind of wave, maybe in the ether? That was more the German perspective at the time.
So where did the proof start? Wasn't there an early experiment with a shadow?
Ah, yes. Sir William Crookes. He put a little Maltese cross made of mica inside the tube.
Oh, okay.
And these cathode rays, whatever they were, travel straight from the cathode and cast a distinct shadow on the glowing end of the tube.
So that suggested particles moving in straight lines, like tiny bullets.
Exactly. It looked like particle motion. But, a shadow isn't quite definitive proof of what it is, just how it moves.
Fair enough. So how did they confirm these things actually carried an electric charge?
Well, the first solid evidence came from magnets. The rays bent when a magnet was brought near, just like a movie negative charge should.
Okay, that makes sense.
And then Jean Perrin really nailed it down. He actually used a magnet to bend the rays directly into a collector, like a small metal cup inside the tube. And sure enough, the cup collected a negative charge. Pretty conclusive.
So negative charge confirmed by magnetism, but the electric field test, that didn't work initially, did it? Why not?
No, it failed for a while. The problem was the cathode rays themselves were actually ionizing the small amount of gas still in the tube.
Creating like a mini conductor inside?
Precisely. It basically created a shield, a conductive plasma, that canceled out the external electric field they were trying to apply.
Ah, okay. So how did Thomson get around that?
He realized he needed a much, much better vacuum. A highly exhausted tube, as he put it.
Less gas to ionize.
Exactly. And with that vastly improved vacuum, then he could finally use an electric field to deflect the rays, confirming, yet again, that they carried a negative charge.
Okay, so negatively charged particles confirmed. Now, defining what this particle was that needed its speed, right?
Yeah.
How did he measure that?
Right, the velocity. This was quite ingenious. He set up opposing magnetic and electric fields.
So one pushing one way, the other pulling the other way?
Essentially, yes. He adjusted the strength of the magnetic field, H, and the electric field, X, until their forces on the particle canceled each other out perfectly.
Meaning the ray just went straight through, undeflected.
Correct. And because the forces were balanced, the magnetic force half equals the electric force $6, he could calculate the velocity simply as x/h/h/rex.
And the speed he found was, well, it wasn't slow, was it?
Not at all. It was staggering. He measured velocities anywhere from 5,000 miles per second up to something like 60,000 miles per second.
60,000 miles per second. That's what, nearly a third the speed of light?
Up to a third, yeah. Unbelievably fast for anything thought to have mass back then.
Okay, incredible speed established. Now, how does knowing the speed help you figure out what this particle is? How do you get its identity?
That's the next crucial step. With the velocity known, he could then turn off the magnetic field and just apply the electric field.
Right.
And then he measured how much the path of the particle bent the deflection. He actually likened it to calculating the path of a bullet shot horizontally that falls under gravity.
Using that deflection and the known velocity.
He could calculate the ratio of the particle's charge to its mass, the famous Tyndall ratio.
And the result here was the real bombshell, wasn't it? Two things stood out.
Absolutely. First, this $n value, it was always the same. Didn't matter what gas was in the tube. Didn't matter what metal the electrodes were made of.
Always $1 7 times 177 in the units they used. It pointed to something universal.
Yes. And second, compare that number. The largest $n ratio known before this was for the hydrogen ion during electrolysis. That was only about 104th Thor hour.
So the corpuscles ratio was, wow, 1,700 times bigger.
1,700 times. That huge difference left only two possibilities. Either the charge on this corpuscle was enormous or its mass had to be incredibly tiny.
So the final piece of the puzzle was to measure the charge itself. How'd they manage that?
They used a recent discovery by C.T.R. Wilson. He'd found that charged particles could act as sort of seeds or nuclei for water vapor to condense around.
Forming tiny visible water droplets?
Exactly. You could literally see the path of these charged particles. Then A.J. Wilson refined this.
Okay.
He measured how fast these charged droplets fell under gravity to figure out their weight. Then he applied an upward electric field just strong enough to stop the drop from falling balancing the electric force against the weight.
Letting him calculate the charge, $1.
Precisely. And the charge $1 on a single corpuscle turned out to be basically the same as the known charge on a single hydrogen ion.
The exact same charge. So if equals,
then the only way for the N ratio to be 1,700 times larger than the hydrogen ion's EM ratio
is if the mass of the corpuscle is 1,700 times smaller than the mass of a hydrogen atom.
Bingo. The mass $1 was about $11,700 of the hydrogen atom's mass. The atom wasn't fundamental. It had smaller parts.
And these corpuscles, they weren't rare.
Not at all. Thomson showed they were emitted by hot metals, by certain metals hit by light, even by radioactive stuff like radium. They were, as he said, one of the bricks of which atoms are built up. Universal.
So a truly groundbreaking series of experiments proving that negative electricity comes in these tiny universal particle packages electrons.
Definitely. But Thomson himself pointed out something else really important in that lecture.
Oh, what was that?
He specifically said that while negative electricity is always carried by these identical corpuscles, the situation for positive electricity carriers seemed entirely different.
Entirely different, implying the positive charge wasn't carried by a lightweight universal particle like the electron.
Exactly. It suggests that the positive part of the atom must be much heavier, much less mobile. It really sets the stage, for figuring out the rest of the atom's structure, eventually leading to the idea of the nucleus. That difference is key.